Okay, hello, good evening. Let's begin with this session today. So we'll take question number 20 of the series. So we are given one equation that is 2 times modulus of 2 times x square plus 1 over x square plus modulus of 1 minus x square, and this is equal to 4. We can multiply inside, so 6 minus this will be 2 to the power, and then x square minus 1 plus 1 over, again take it inside, so 2 to the power x square minus 1. Now, of course, this is a exponential equation with modulus, so we cannot generally solve this. So we'll try to see the range first. So if I look at this thing by AMGM inequality, I'm going to get this thing is greater than or equal to 2, and this thing is always positive. And again, the same story here also, greater than or equal to 2 by AMGM. So by AMGM inequality, we get this, and now we see that RHS. So this quantity is greater than or equal to 2, with minus this is going to be less than or equal to minus 2. And then 6 minus 2 is going to be less than or equal to 4. So RHS is less than or equal to 4. And LHS is 2 into 2 is 4 and then positive. So our LHS is going to be greater than or equal to 4. So this implies for the solution, they meet at 4. So for the solution, they meet at 4. So when they meet at 4, which means this quantity should achieve its minimum, which is x square minus 1 should be equal to 0, or you could say that both of them should be equal. Okay. So x square minus 1 should be 0, which means x square is equal to 1, and that is x is equal to minus 1 comma 1. So now we'll set it up here. So I have x1 plus x2, the lower limit for this integration, which is minus 1 plus 1 is 0. And then 3x2 minus x1 was going to give me 3 plus 1, which is 4. So my integral setup is ready from 0 to 4. So let's see. That means I'm going to integrate from 0 to 4, the fractional part of x over 4 into 1 plus GIF of tan of plus GIF of tan of fractional part of x over 1 plus fractional part of x and then dx. So since we want to see the behavior of this tan of this function, that means I'll consider finding the range of, so we find the range of the nested function, this one. So I'll consider a fractional part of x over 1 plus fractional part of x. This could be further written as 1 minus 1 over 1 plus fractional part of x. So now this can be further, I need to find out the range here. So since fractional part of x always belongs to 0 to 1, which means fractional part of x plus 1 will belong to 1 to 2. I'll take the reciprocal. So this is going to belong to half to 1. And then with negative, I'm going to have here minus 1 over fractional part of x plus 1 belong to minus 1 will be closed. So this would be closed, and then from minus 1 to minus half open. So now if I add 1, so I get 1 minus 1 over 1 plus fractional part of x belongs to, this is going to be 0, but this is going to be half. So I get this entire quantity in between 0 to half. So we know that the tan of this is going to be less than 1, because tan becomes 1 at pi by 4. So this implies the GIF of tan of fractional part of x over 1 plus fractional part of x is equal to 0. And also x belongs to 0 to 4. So my x over 4 belongs to 0 to 1. So when any quantity belongs to 0 to 1, so its fractional part will be same as itself. So that means now this integration turns out to be simply integral 0 to 4 just x over 4 into 1 plus 0, which is 1 over 4 will be down, and then simply x square integral, no, not integral, limit x square over 2, and then from 0 to 4. So this is going to be 1 over 8 here. And then 4 square will be 16 minus 0. So this turns out to be 2. So 1 over 4 is constant. X integration is x square by 2. Upper limit is 4 square. So 16 minus 0. So answer will turn out to be 2. So we get here answer as 2. Now let's go for the next one. So look at, we are given a polynomial satisfying the relation f of x plus 1 minus p times f of x is equal to 3 for all x belonging to R. And now they're saying that p is any real number. And the leading coefficient of f of x is 2, then value of whatever they ask. So this line is enough. We have a polynomial. So if I consider a polynomial and I go on composing with itself, so the degree of polynomial. So if I have f of x is a polynomial, f of x is a polynomial, say of degree n, then f of x, degree of f of x is going to be strictly more than n, right? And now we see that here, this is composed 3 times. That means this degree will be definitely more than this. And when I add this polynomial, okay, of course, degree won't decrease here. Okay, degree won't decrease because f of x has degree more than f. So if I add it or subtract it, it's not going to, the highest term is not going to go. That means I cannot get constant on the right side. So this is possible only when f is linear. So if f is linear, this implies what should happen? F of x must be equal to 2x plus some constant. And it's only because of the leading coefficient is 2. So we have taken f of x is equal to 2x plus c. Now consider f of x. So this is going to give me 2 times f of x plus c, which is 2 times f of x is 2x plus c, which is 4x plus 3c. And then we have here f of x, which means we have f of here we'll write down 4 times f of x plus 3c. That is 4 times 2x plus c plus 3c. And this will give me 8x plus 4 plus 3 is 7c. And now I'll consider that equation. So I have here 8x plus 7c plus 1 minus p times f of x is 2x plus c is equal to 3. So if I open this, I have here 8x plus 7c plus 2x plus c minus 2px and then minus pc is equal to 3. So 8 plus 2 is going to be 10 minus 2p into x. Then constant is 7c minus pc. So no, 8c minus pc. So 8c minus pc is equal to 3. That's what we get. And now if we compare these two polynomials, of course, this is going to be 0. So I have here 10 minus 2p turning to be 0. And this this portion, that is 8c minus pc, will take the responsibility of 3. So I'll take c common rather. I'll be having here 8 minus p into c is equal to 3. So from here I get p is equal to 5. So p is equal to 5. I plug in here, I get c is equal to 1. So therefore my polynomial is simply 2x plus 1. This is my polynomial. F of x is 2x plus 1 and p is equal to 5. So we want the derivative of f of x at x is equal to p. So I'll find out f of x rather. I already have it here. So no, I don't have, I guess. Oh no, we're lucky. So we have here 4x plus 3c. So 4x plus 3c I have. 4x plus 3c, so it means 4x plus 3c is going to be here 3. So I have this thing, and now I want the derivative. So if I differentiate it on both sides, so I get simply 4. Now it does not matter at what point I find out because the derivative turned out to be constant. So even at p is equal to 5, I'm going to get 4. And the next portion is to find the inverse and then integrate it from -5 to 5. So minus 5 to 5 f inverse. So f inverse is going to be y minus 1 over 2 is equal to x. So this implies f inverse of x is equal to x minus 1 over 2. So this implies 2 times f inverse of x plus 1 is equal to x. And that is what being demanded in the integral part. So 2f inverse plus 1. So which means I can just plug in here simply x dx, and this is 0. So the final answer would be only this much, which is 4. So the answer would be, let's go ahead for the next. Now looking at this. So we have a twice differentiable function satisfying f of x is equal to 1 minus x. And then this integral is given to be j equal to 0 to 1 f of x. So since we don't know the function so far, and we have f double dash of 4 by 5 is 0. Okay, so then we have to see which of the following option is true. So let's go ahead. So I have f of x is equal to 1 minus x. Now I need to find out the functional or try to get the equation here so that we can easily get it. So here gets the idea. That means if I replace here, if I'm going to replace x by f of x. So if I do this thing, I'm going to have here f of x would be equal to 1 minus f of x. Now f of x is nothing but 1 minus x. So 1 minus f of x. That means I'm going to have here f of 1 minus x plus f of x is equal to 1. So this part I saved directly. And now what happens is we can set x is equal to 1 by 3 here. So when I set x is equal to 1 by 3, I'm going to have f of 1 minus 1 by 3 is 2 by 3 plus f of 1 by 3 is equal to 1. And this makes my option A correct. Now going further. Okay, so I'll integrate this one from 0 to 1 basically. So also 0 to 1 f of 1 minus x plus integral 0 to 1 f of x dx is going to be 1. So 0 to 1 f of 1 minus x is same as 0 to x f of x using the King's property. So that means I'm going to get here 2 times integral 0 to 1 f of x dx is equal to 1, which means integral 0 to 1 f of x dx is going to be half. So here we have used King's. Now further, we need to talk about f dash and f double dash. So let's go ahead. So I have f of 1 minus x plus f of x is equal to 1. So I'm going to differentiate this with respect to x. So I'm going to have here f dash of 1 minus x and then one more minus plus f dash of x is equal to 0. So which means I have f dash of x is equal to f dash of 1 minus x. Now, since they're talking about the interval 1 over 4 and 3 over 4, so I can plug in x is equal to 1 over 4. So if I plug in x is equal to 1 over 4, I'm going to get here f dash of 1 over 4 is equal to f dash of 3 over 4. So now f is thrice differentiable function, which means f is continuous. And also we see that f dash of 1 over 4 is same as f dash of 3 over 4. So we can apply Rolle's theorem. So by Rolle's theorem, there exists some c between 1 over 4 to 3 over 4 such that its double derivative is 0. So f double dash of c is 0. That means there exists at least one real root in 1 over 4 to 3 over 4 for f double dash. So c is also correct. And now we have f double dash of x is equal to 0, at least one root in 1 over 2 to 4 over 5. So this part we have to handle carefully. So now what we will do, now this is for f triple dash basically, the correct question. So now if I consider here f double dash, I'll differentiate this one again. So if I differentiate it, I'm going to get here f double dash of 1 minus x now, and then plus f double dash of x is equal to 0. This is what I get. And now what happens here, for the double dash, I'm going to send it here. So f double dash of 1 minus x is going to be minus of f double dash of x. And now since the value they have given already, so I'll plug in x is equal to half. So we need to deal with half to 4 by 5. So set x is equal to half. So in this case, I'm going to have here f dash of half is equal to minus of f double dash of half, which means f double dash of half is what? 0. So f double dash of half is 0. And they have given that f double dash of 4 by 5 is also 0. So again, I can apply Rolle's theorem. So therefore, by Rolle's theorem. Rolle's theorem we can apply in 1 over 2 to 4 over 5. So again, there exists some C1 belonging to half to 4 over 5, such that f triple C1 is 0. That means there exists a root for the third derivative as well. So D option is also true. Since the correct question is f triple dash. Okay, this is a problem from GRV Bansal book, chapter 5, differential integration. And if you go with the question which we had written here, then they would be incorrect, because it's talking about f double dash. So for f double dash, we don't have anything here. Now let's go ahead for the next question. So we have another one here. Now this is for minus infinity to infinity. We have e to the power tx into f of x dx is given to be a sine inverse of t minus 1 over root 2 for all the t belonging to minus 1 plus root 2 and then 1 plus 1 by root 2. So we need the value of 2 root 2 integral minus infinity to infinity x into f of x dx. That is required. So of course, now if I treat this function of t and then differentiate partially with respect to t partially. So basically what happens here is this would become the integration under differentiation under integral sign. So I'm going to have here minus infinity to infinity del over del t of e to the power tx into f of x dx is equal to again del over del t of sine inverse of t minus 1 over root 2. So for this portion, I'm going to have minus infinity to infinity, and then e to the power tx would be as it is, and then again derivative of tx, which is x, that's constant. This is going to give me the derivative of sine inverse, which is 1 over square root of 1 minus t minus 1 over root 2 square. I'm going to have this. Now, next part is we need to find out the integration from minus infinity to infinity x into f of x. So this part I have observed. That means I need to get rid of this e to the power tx. So we will set t is equal to 0. So the moment I set t is equal to 0, I get minus infinity to infinity x into f of x dx is equal to, on the right side, I'm going to get here 1 over 1 minus half, which is going to be 1 over 1 over 2, which is root 2. So therefore, if I multiply 2 root 2 here, so this gives me simply 2 root 2 into root 2. That turns out to be 4. So the answer would be 4 for this problem. Let's go ahead for the next one. So now we have, again, f of x is equal to limit n tends to infinity and then cos x over 1 plus tan inverse of x to the power n. So now the entire problem will now be focused on tan inverse of x. So here we have to do cases. So case 1 is tan inverse of x is going to be less than 1. It's modulus basically. Modulus is less than 1 is case 1. Case 2 is modulus of tan inverse of x. It's going to be more than 1. The third case is going to be tan inverse of x is going to be 1. So now the three cases. Now if I go ahead, then I have mod of tan inverse of x is less than 1. So for this thing, what we will do, we'll just graph the tan inverse of x basically. So if I consider this tan inverse of x, because we have to extract the function, so we should know the behavior, what will happen exactly. So tan inverse of x, if I draw, and this is going to be this way. No. So if you see here, a tan inverse of x is going to be less than 1. So this implies if I consider only more than 1, the same thing I'm going to get here for this one also. So consider tan inverse of x to be more than 1. So if I'm saying that my tan inverse of x is more than 1, which means there would be here somewhere. Now we are saying this is more than 1. So this point I need to see what is this. So that means tan inverse of x we know already it's from minus pi by 2 to pi by 2, the max limit. So since tan inverse of x belongs to what? Pi by 2 to minus pi by 2 to pi by 2. Belongs to minus pi by 2 to pi by 2, which means my tan inverse of x actually after this thing is going to belong to 1 to pi by 2. So of course this is bijection. That means I can take the inverse on both sides. So I'm going to have here x belongs to what? Tan 1 to infinity. So I get this part. And similarly for tan inverse of x less than minus 1, because mod will open with two things. So I have here tan inverse of x less than minus 1. So of course that means tan inverse of x again belongs to negative pi by 2 to minus 1. So that means my x will belong to minus infinity to minus tan 1. I'm going to get here. And then this quantity, we know it's going to be between minus tan 1 to tan 1. So let's go ahead. This is case 2. And then case 3 is mod of tan inverse of x is going to be less than 1. So which is minus 1 is less than tan inverse of x is less than 1. So we are saying my tan inverse is between minus 1 to 1. So of course this is from minus pi by 2 to pi by 2. That means we have no objection. So we'll write down here my x belong to what? Minus tan 1 to tan 1. So that means my now integration would be divided. So I'll be having, in this case, when my tan inverse of x is more than 1, so when my tan inverse of x is more than 1, that means its power n will go to infinity. So which means I'll consider my function here f of x is equal to what? So limit n tends to infinity. This is cos x over 1 plus tan inverse of x to the power n. So for the first case I'm doing, it's the case 1, when mod of tan inverse of x is less than 1. So in this regard, I'm going to have here tan inverse of x to the power n will go to, because mod is less than 1, so this becomes a geometric GP with common ratio less than 1. So this will converge to 0. And in this case, this will go to infinity. So I can have here 1 over tan inverse of x to the power n going to 0. And for this, I'm going to be here, of course, x is equal to tan 1 and minus 1. Now, if we consider these three things, so in case 1, if I consider, so for case 1, this is going to give me, simply this is going to be 0. That means I'm going to have here cos x. This will happen when my x belong to what? Minus tan 1 to tan 1. This is my case 1. And case 2 is tan inverse of x is more than 1. So again, f of x is going to be what? Now I'm going to divide it by tan inverse of x, because this will take care of the infinity part. So this is going to be here, and then same thing here. So tan inverse of x to the power n plus 1. So this is going to give me 0 when my x belong to minus infinity to minus tan 1 union tan 1 to infinity. And when this is going to be tan 1 basically here, when my x is tan 1, so we have 1 to the power n, which is going to be 1 only. So I get here cos x over 2, but this is not even included. So let's go ahead. Now my function is from 0 to infinity f of x dx. So 0 to infinity f of x dx will now be partitioned into 0 to tan 1 f of x dx. So the left part we won't consider because that's not in the domain. So this portion won't be coming. But this portion will come as 0. So we have to consider. So from minus tan 1 to tan 1, I have this thing. That means I can consider from 0 to tan 1 at least. So 0 to tan 1, I have cos x. So 0 to tan 1, I'll be having cos x. My God. Okay, no charge. 1 minute. Okay, so we're back. So 0 to tan 1 f of x dx, and then this would be again from tan 1 to infinity. So tan 1 to infinity, I'll be considering this portion. So tan 1 to infinity, this is going to be 0. So tan 1 to infinity f of x dx. So now 0 to tan 1, my function is cos x. And then from tan 1 to infinity, this is going to be 0. Now this turns out to be simply cos integration, which is sine x. And then this is from 0 to tan 1. And this guy would be bye-bye. So we get sine of tan 1 minus sine of 0 is gone. So the answer would be simply sine of tan 1. So this is going to be sine of tan 1. Let's go for the next one.